Now to apply our newfound knowledge to integrals. Let's start with line integrals. Here we have a curve oriented, and we want to take an integral of a scalar function over it. S always stands for the arc length parameter. If you're dragging a tape measure behind you, that's S. We'll just be looking at Riemann sums. So I'm taking a partition and adding up the chunks of the partition. Of course, this isn't really defined yet because the pieces I'm adding, my little partition pieces, are curve chunks. This is a key point in all Riemann integration, and it's true in all integration, is that you can replace by linear approximations, because all error terms then are delta squared terms, which go away in the limit. So I've got one little chunk of curve from my partition. And I'll use the parameterization with another variable. I'll parameterize in t, for instance. So t1 and t2 go to the points x1 and x2. Now, like we did before, we'll take a point and a vector pair, which goes to a point and a tangent vector. Here I'm scaling by dt. So the corresponding output vector is scaled as well. I want the length of that, the magnitude of the vector. Plugging in the parameterization and replacing delta S by its linear approximation, I have a Calc 1 Riemann sum. So I turned a Calc 3 line integral into a Calc 1 integral. This is called the pullback. I've pulled it back from space into a Calc 1 setting. And then I take the result and I push that forward. This is called the Jacobian. Driving to the limit, I'm integrating over the parameter domain. And there's my Calc 1 integral. Now, as before, we'll just put two of these together for the area integral. And since we have area integrals, it's exactly the same as volume integrals. Just keep on adding pieces. So I have a domain in 2 space. I have a scalar function. I want to integrate that scalar function over the domain. It's common to get rid of all the multiple integrals at this point because we're doing n dimensions. So I have a domain in R2, which I can parameterize. Every point in that domain has a T1, T2 parameter that belongs to it, and that's over its own region in the parameter space. Point, basis vectors, standard basis, then gets mapped over through the parameterization. to tangent vectors to the parameter curves. Columns of the matrix are tangent vectors. Now, as before, we'll scale. So I just want a little chunk in each piece, which scales the output tangent vectors. Looking at close-up, I've got my parameter curves, parameterizing the domain, my dA chunk, and then I'm going to replace it with a linear approximation, the area of that little parallelogram piece. That's my linear approximation. Curves of one variable and curves of one variable. So the vector I'm feeding in to the derivative, evaluated at 1, 2. There's the output vector. The area is the determinant. We're taking the absolute value of that because we want it to be positive. And now I'm back to iterated integrals, to Calc 1 integrals. There's my pullback from space and my push forward and my Jacobian. Integrating over the parameter space, integrating in space itself.